So today's lesson is going to be on higher order derivatives. So what does that even mean, higher order derivatives? Let's go back to figuring out what a derivative means. Well, we looked at a derivative by finding the limit of the difference quotient. The difference quotient analyzes some sort of rate of change, right? Whether it's a tangent or a secant, the slope of that, a secant or tangent, was figuring out either for the secant an average rate of change or for the tangent an instantaneous rate of change. So if your graph, for example, on the y-axis is measuring position and on the x-axis time, you have a graph of position time. The rate of change for position time tells you velocity, meaning if you find the derivative of position, you get velocity. Similarly, if you were to then find the rate of change of velocity, we call that acceleration. So acceleration is the derivative of velocity. And since velocity is the derivative of position, acceleration, we say, is the second derivative of position. And we denote that with 2 primes. Now we can also write this in Leibniz notation, which looks like this. You would say a derivative of a derivative, okay, we have as d squared y over dx squared. And again, Newtonian notation would have 2 dots. Alright, so if we were to try an example then, here we have a medieval prince trapped in a castle, wraps a message around a rock and throws it from the top of the castle wall to the far side of the castle's moat. The position of the rock is given by this function. Determine the derivative of that function. Okay, well, s prime of t is going to equal, it's just a polynomial function, so we could just apply the power rule for each term. So bring the 2 out in front, we'll get minus 9.8 times time. And this is just power of 1, so plus 8. And 9.5 is a constant, so it's gone. So there it is. What does this derivative represent? That's the velocity with respect to time. Okay, part 2 says find the derivative of that derivative. Okay. So find the derivative of velocity. Well, the 8 becomes 0 because it's just a constant. And here, this is t to the power of 1, so multiplied by 1, and we just get minus 9.8. That's it. And what does that represent? The acceleration. And that makes sense, because the acceleration should be minus 9.8. That's what gravity is here on Earth. Unless this medieval prince is on another planet. But here I have a sketch of our graphs. So here we have position time graph, which makes sense, right? We're throwing something. And here I have the first derivative. And the second derivative isn't on here, but it would be a horizontal line. It only goes to -2. So somewhere down here at minus 9.8 would just be a horizontal line, and that would be our second derivative. So that's a of t. Now notice, so what is the value of the derivative or of velocity when position is at a maximum? So when position reaches its peak, right there, velocity is at 0. All right. What does this mean from a physics concept? It means that poor prince just threw the message straight up instead of throwing it across. Right? It's all right. He's not going to get much help. And so he throws the message in the bottle straight up instead of across the moat. Good try, though. Good try. Because once it reached its peak, its velocity is 0. Or perhaps this is just the position, the vertical position only. All right, let's go to the next question. What is the sign of the derivative at a time before the maximum? So before the maximum would have been here. Here's before the maximum. And so the derivative is somewhere here. So that's a positive sign. Okay. Now if it's a positive sign, is the object speeding up or slowing down? Here's how you tell. The acceleration is negative, and the velocity is positive. So if you take acceleration and multiply it by velocity, if that is going to be a positive value, then you're speeding up. However, if you take acceleration and multiply it by velocity, and that's going to be a negative value, you're slowing down. So in this case, acceleration is negative, meaning if velocity is positive, multiply a positive with a negative, you get a negative. So that's less than 0. So in this case, we're slowing down. All right, well, what's the sign of that first derivative, or the velocity after the maximum? So at this point, well, it's right down here. So it's a negative. So is it speeding up or slowing down? Well, if it's negative and acceleration is negative, 2 negatives gives you a positive. So it's greater than 0. So we're speeding up. So our first example says determine the second derivative of this function, f at x equals x over 1 plus x, when x equals 1. Okay, well, let's start with the first derivative. This here looks like a quotient rule. I mean, there's different strategies you can take, but I'm going to do the quotient rule. I think that's going to be the easiest for us. So we start by taking the derivative of the numerator, which is 1, and multiplying by the denominator. So I'm just going to have that as 1 plus x. Then we're going to subtract the numerator, which is x, and multiply that by the derivative of the denominator, which is just 1. All right, so that's all we have there. And divide that by the denominator, 1 plus x squared. Okay, well, in the numerator, we end up having x minus x. So those are going to go away, and we just get 1 over 1 plus x squared. So there's our first derivative. Okay, well, let's find the derivative of this. So to figure out what that second derivative is. Now, if you wanted to, you could just write this as a negative exponent, or you can do the quotient rule, whichever. So the square, we wanted to keep that on the outside of the bracket. So that is just 1 plus x to the minus 2. Okay, so the derivative of that then is just bring the minus 2 out in front, times 1 plus x, subtract 1, so minus 3, times the derivative of inside the bracket, which is just 1. So that gives us minus 2 over 1 plus x to the 3, power of 3. Okay, now that we have that, the question still wants to know what it is when x equals 1. So we're going to find the second derivative at 1. And that's just going to be minus 2. If we put 1 in here, you get 1 plus 1, which is 2. So 2 cubed. So minus 2 over 2 cubed. Right? You can cross 1 out and make it a squared. So you just have minus 1 quarter. So our second question says, the position of an object moving on a line is given by this function, where s is in meters and t is in seconds. Determine the velocity and acceleration of the object as t equals 2. Okay. I'm going to write this over here, even though it's not the third question. Here, I'll put a line. So we have s of t. If you want to find the velocity, well, the velocity is the first derivative of position. So we need to find the derivative of this. Just a power rule for a polynomial. So bring the 2 out in front, so we have 12t. Subtract 1 from the exponent, so just a 1. And then again, bring the 3 out in front, so 3t, and subtract 1 from the exponent, so a 2. So there's your first derivative. So there's velocity with respect to time. And if we want to know what that is at 2, simply sub in 2. So you get 12 times 2 minus 3 times 2 squared, which is 24 minus 4 times 3 is 12. So 24 minus 12, which is just 12 meters per second. Now, if you wanted to find the acceleration, then we need to find the derivative of velocity time. Acceleration equals derivative of vt. So that is also just the second derivative of position. Which is just apply the power rule to this one. So 12t just becomes 12 minus, bring the 2 in front, so 2 times 3 is 6, and subtract 1 from the exponent. And if we want to find out what that value is as 2, just substitute 2 in for t. And at that time, we get a 0 acceleration. Now part B says, at what time is the object at rest? Okay, to figure out when it's going to be at rest, well, that's asking about velocity, and it's asking for time. So what we're going to do is take our velocity function, which we've already solved for up here. So 12t minus 3t squared, and we're going to set it equal to 0, because we know, or we want to know, when the velocity is 0. So let's solve for time then. So we are going to factor out a negative 3t, which leaves us with t minus 4, which equals 0. So two options. T could be 0, and t can be 4 seconds. So at 0 seconds and 4 seconds, our velocity is 0. Next question says, in which direction is the object moving at t equals 5? Okay, so if you want to know direction, then we have to look at velocity again. A different color. So this was B, and let's go do C. So we're going to figure out what the velocity is at 5. So we're going to substitute 5 into our velocity function. So 12 times 5 minus 3 times 5 squared. And that gives us minus 15 meters per second. So if you remember vectors, the negative tells you a direction. And so in this case, all we're going to say is negative direction. That's its direction, negative direction. D says, when is the object moving in a positive direction? Okay. Well, let's go look at this again. So we're going to look at velocity again, and here I factored velocity. So I have it as minus 3t times t minus 4. But what we want to know is, when is it moving in a positive direction? So when is this going to be greater than 0? Well, I can just divide both sides by 3 and write minus t times t minus 4 is greater than 0. If I divide both sides by a negative, then I will switch the sign and say, when is it less than 0? So when is this less than 0? Well, let's look. If t is less than 0, we get a negative here, and we get a negative here. So two negatives is going to be a positive. So it's not going to be less than 0. What if t is greater than 4? Well, that's a positive value. But in the bracket will also be a positive value, so that's not going to be a negative. Well, what if t is between 0 and 4? Well, this will be positive, and this will be negative. So that's what we want. So therefore, t is between 0 and 4. That's when the velocity will have a positive value. Now, the reason why I was looking at options less than 0, options more than 0, and options between 0 and 4 is because I know that the velocity is 0 at t equals 0 and 4. Right? So what that means is if you had some graph, let me just look at one example. If you have the velocity time graph past 0, it means it's very possible that before it was either positive or negative, and after it's either positive or negative. And it could do something like this. This isn't an example for our case, this is just some random example. But when it's 0, before and after 0, it's going to be either positive or negative. So that's where I was sort of looking. So in this case, I was looking at, okay, well, before 0, what is it? And if we substitute any number before 0, well, take -1 for example. -1 times, well, -1 minus 4 is -5. So 2 negatives gives you a positive value. So that's definitely not less than 0. All right. What if you picked a number greater than 4, like 5? Well, here you have 5. And 5 minus 4 would be 1. So 5 times 1 is definitely not less than 0. Well, what about a number between 0 and 4, like 2? Well, here you have 2. And 2 minus 4 is -2. So that's a positive times a negative. That is less than 0. So that's what we're looking for. So that's how I sort of figured out the range of that. All right, so last one, part E, says, when does the object return to its initial position? So if we're talking about position, we care about s of t. And it gave us this function as, sorry, not minus. So it's 6t squared minus t cubed. So when does it return to its initial position? That's when this is all going to equal 0. Okay, so let's factor out. I can factor out a t squared. And that's going to give us 6 minus t equals 0. Now obviously t equals 0 is a solution because that's where it started. But the question isn't asking where it started. It's asking when does it return to that starting point. And it looks like another solution would be t equals 6 seconds. So that's the one we care about. Alright, so the last example says a baseball is hit vertically upwards. The position function, st, in meters of a ball above the ground is minus 5t squared plus 30t plus 1, where t is in seconds. First, determine the maximum height reached by the ball. So how do I do that? Well, I know that this is a minus t squared, so I know the quadratic's going to look something like this. It's going to open down. Now the maximum height would be right there, and that is where the velocity is going to be 0 because the tangent there is horizontal. So determine the maximum height of the ball. First I need to figure out where, sorry, not where, but when that occurs. And I can do that by first finding the velocity, which is the first derivative of position. So that's going to be, I'll bring the 2 out in front, so we have minus 10t plus 30. Okay, so I want to know when this is going to equal 0. So I can rearrange it. You can have 10t equals 30, or t equals 3. 3 seconds. Okay, so after 3 seconds, the position is going to be at its maximum height. But it says, what is that maximum height? Well, I'm just going to plug in 3 into the position to figure out what that value is at a time 3. So that's going to be minus 5 times 3 squared plus 30 times 3 plus 1, which is 46 meters. So the second part says determine the velocity of the ball when it is caught 1 meter above the ground. Okay, so when is it caught? That's what I need. I have a function for the velocity here, but I need to know at what time is it caught at. Well, since I know where it's caught, what I can do here is look at the position function, s of t, which we know is minus 5t squared plus 30t plus 1. Okay, it's caught 1 meter above the ground. So let me set that position function equal to 1. So I'm going to write 1 equals minus 5t squared plus 30t plus 1. Okay, if I bring the 1 over, I get 1 minus 1. So we end up with 0 equals, and let's factor out a minus 5t times by t minus 6. So t can be 2 possible values. It could be 0, but that's not when it's caught. This is when it's hit. Right? It's hit right at time 0. Another option for t is t equals 6. So this one must be when it is caught. So I know it's caught at a time t equals 6. What's the speed of that? Well, let's go back to our velocity function, which is minus 10t plus 30. And I want to know the speed at 6 seconds. So that's minus 10 times 6 plus 30. And we get negative 30 meters per second. Or if you want, if you remember vectors, that just means 30 meters per second down.